It falls from the sky. It makes up 60% of our bodies, and just about every chemical process related to life takes place with it or in it. Dihydrogen monoxide. Without it, none of the chemical reactions that keep you alive would happen. None of the reactions that sustain any life form on Earth would happen. Not even the majority of inorganic chemical reactions that shape the surface of the Earth would happen. Water is the key to nearly everything, and one of the reasons it's the key is because it's really good at dissolving stuff. We need it so bad that we dump over 180 gallons of it into our bodies every year, and we do that in order to maintain an aqueous or water-based solution inside our cells, because aqueous environments are pretty much the best for cool chemistry. Each and every one of us uses water for all kinds of chemistry every single day. Our body chemistry, our food chemistry, and yes, our laundry chemistry all take place in water. Ugh. This used to be a white sock. It is now a little bit of a gray sock, and in places a little bit of a yellow sock. But anyway, I want it to be white again, and to do that, I'm gonna need some chemistry. To whiten whites, you might use a solution of sodium hypochlorite, better known as bleach. What makes bleach so good at its job is that it's a really strong oxidizer, meaning that the oxygen atom is really good at pulling electrons away from other compounds, making them break apart. This is really handy for getting rid of stains, but as you can tell by the formula, sodium hypochlorite also contains chlorine, which happens to be really good at killing things. That's why we use it in swimming pools and as a disinfectant. But there are lots of other good oxidizing agents, and one that doesn't contain chlorine is hydrogen peroxide, and it can be used as a bleach too, but its only components are hydrogen and oxygen, just like water. We'll talk about oxidation and other kinds of reactions in a couple weeks, but before we get to that, you have to understand solutions. And before we do that, I'm just gonna get rid of the laundry because it's kind of stinky. This bottle of hydrogen peroxide contains a solution. And not just the solution to my problem of stained laundry. By solution, I mean a solution of liquid with another substance dissolved in it. Here, water is the liquid or solvent, and hydrogen peroxide is the solute or dissolved material. And water is an amazing solvent, possibly, arguably, the best solvent on Earth. Why? A lot of reasons. There's a lot of it on the surface of the Earth. That helps. Just abundance is good. It's liquid at a very wide range of temperatures, and being liquid is what you need to be able to be a solvent. But also because it's polar. It's a very polar molecule. Remember how I said that oxygen is really good at pulling electrons toward it? Well, oxygen atoms are more electronegative than hydrogen. The oxygen atom pulls harder on the molecule's electrons than the hydrogen does. As a result, the electrons in a water molecule tend to spend most of their time near the oxygen, giving the oxygen end a partial negative charge and the hydrogens a somewhat positive charge. This polarity makes water extremely effective at dissolving things, especially other polar things. The sugar we mixed into our tea last week, for example, was polar. When you mix a polar solid like sugar into a polar liquid like water, the molecules of the water surround the sugar molecules. The negative side of the water molecule is attracted to the positive side of the sugar molecule, and vice versa. In interacting with the sugar molecules, the water inserts itself between all of the individual molecules of the sugar that were once clumped together in the sugar crystals. A liter of water can dissolve as much as 1,800 grams of sucrose. Water-based solutions. Earlier, I called them aqueous solutions, and I'm calling it an aqueous solution again so that you remember it's called an aqueous solution. Aqueous. You could create all sorts of aqueous solutions using salts or minerals, even acids. Ethanol, which composes 95% of this grain alcohol, is polar, so it dissolves easily in water. But water does not dissolve non-ionic, non-polar substances. Oil, for instance, doesn't have any polarity, so it has no interest in interacting with water. So when you mix them, they separate. Water's polarity also gives it lots of other super useful properties. For example, water can decrease the attraction between ions of different charges. We call this its dielectric property. Take table salt, for example. It's made of positively charged sodium ions and negatively charged chlorine ions. When it's mixed with water, the water dissolves the salt into its component ions. The water molecules then surround the individual ions and shield them from each other's electric charges. These ions in water are called electrolytes, literally loosened electricity, because separating them through dissolution frees them to act independently and carry their electrical charge around. You've probably heard about electrolytes in biology class, but you've definitely heard about electrolytes in Gatorade commercials. Your body needs electrolytes to carry electrical signals that help your muscles twitch and your brain cells fire and get all the business of living done. In addition to helping you live, electrolytes are one of the most important ways chemists have of classifying solutions. Pure water on its own does not conduct electricity, which seems a little weird to us, the whole hair dryer in the bathtub thing still being a terrible idea. But if you put a bit of salt or any other ionic solid in the water, they dissolve into those component electrolytes. It's the electrolytes that are conducting the electricity. It's not what you might expect, but we have Swedish physicist Svante Arrhenius to thank for figuring this out. While doing his doctoral research in the 1880s, he first developed the idea that a solution's electrical conductivity could be linked to the concentration of ions in the solution. It was one of his predecessors, British super genius Michael Faraday, who discovered that substances dissolved in water conduct electric currents. Faraday was terrible at naming stuff, though, so he wrote to a guy who was known for coining terms, William Whewell. You may have heard of his most famous creation, the word scientist. Whewell wrote back to Faraday saying, "I would propose for the two elements resulting from electrolysis the terms anion and cation, and for the two together, you might use the term ions." And there's something interesting here, and I didn't pick up on it at first, but Whewell said the things resulting from electrolysis. Faraday thought that the electric current is what produced the ions. What Arrhenius discovered was that water simply dissolves certain substances, like salts, into their constituent ions, which themselves carry the charge. And since electrolytes carry electric charge, the higher the concentration of electrolytes in a solution, the higher its electrical conductivity. Arrhenius found that you can even reverse engineer your study of a solution and by measuring its electrical conductivity, figure out how concentrated it is. Despite the importance of his work, Arrhenius's chemistry professors didn't think much of it, and he got a mediocre grade, which is why it must have been particularly sweet when he won the Nobel Prize in 1903 for that very same research. Today we know a little bit more about how electrolytes work, and we've learned that the relationships between their concentration and their conductivity is not always straightforward, because not all electrolytes dissolve equally well in water. A strong electrolyte, for example, is one that dissociates or breaks apart completely when dissolved in water and conducts electricity very well. Salts do this, so do strong acids like hydrochloric and sulfuric and nitric acid, as well as strong bases like sodium and potassium hydroxide. Weak electrolytes only dissociate partially when dissolved in water, so they're only somewhat conductive. Most of the solutes molecules stay stuck together, remaining neutral. Acetic acid, the active ingredient in vinegar, and ammonium hydroxide are examples of this. And of course, some things dissolve in water but don't conduct electricity at all because they don't dissociate into ions. Alcohol and sugar, for example, are non-electrolytes. Now, what does any of this have to do with my laundry? Well, hydrogen peroxide is a polar molecule, so it dissolves really well in water. But it's a very weak electrolyte. When it dissolves, it tends to dissociate into a water molecule and a lone oxygen ion. Since the dissolved peroxide creates even more water, the concentration of ions is quite low. But that lone oxygen ion is not happy by itself. It goes on an oxidizing rampage, swiping electrons from anything it can find. It's especially good at tearing up the tricky double bonds that tend to give laundry stains their color. When that rampaging ion destroys the double bond, the stain disappears. We're used to thinking of hydrogen peroxide as a fairly mild chemical, but that's because the over-the-counter stuff is pretty dilute. Too much peroxide could actually dissolve my clothes, and some of my favorite shirts are in here, so we need to dilute this stuff to make the solution the right strength. And as you might expect, if you joined me on my recent foray into stoichiometry, when chemists think about the strength of a solution, they think about moles. So before we can dilute this formula, first we have to figure out how many moles of solute of hydrogen peroxide we're working with here. You'll remember, I hope, that 1 mole of a compound equals 6.022 times 10 to the 23rd molecules. That is a big number. So to make it easy on ourselves, we usually figure out how much a mole of a particular substance weighs. In our case, a mole of hydrogen peroxide weighs 34.04 grams. The number of moles of solute that are in a solution is known as its molar concentration. That's also known as the solution's molarity. As a rule, molarity equals the number of moles in the solute divided by liters of solution. So a 1 molar solution contains 1 mole of solute per 1 liter of solution. Do not confuse this with another another way of measuring concentrations based on mass instead of based on volume. This is known as molality, and it's expressed as the number of moles of a solute in a kilogram of a solution rather than in a liter. Molality refers to moles per unit mass, and molarity refers to moles per unit volume. Sorry, scientists are bad at naming things sometimes. You just have to remember this stuff. So now that we know what molarity is, let's figure out the molarity of this hydrogen peroxide solution. The label on the bottle says a 3% solution weight per volume. Technically, that's terrible chemistry because it's expressing a percentage in terms of two different sorts of units, but it does let us know how much solute went into the solution: 30 grams of H2O2 per 1 liter of water. I mean, just to be clear though, it makes no sense to have a percentage with two different units, and maybe these folks need to watch some Crash Course Chemistry. So to calculate the molarity of this solution, we first need to figure out how many moles of hydrogen peroxide are in 30 grams of hydrogen peroxide. If we divide the 30 grams in the solution by its molar mass of 34.014 grams per mole, we find that we have 0.88 moles of hydrogen peroxide per liter of solution. Or, so you get used to the lingo, a 0.88 molar solution of H2O2 in this little brown bottle. Now that we know the molarity of the original formula, we can start thinking about how to dilute it. To dilute a solution, you either have to add more solvent or reduce the amount of solute. Since I'm already starting with the solution, I need to add even more solvent, water, probably in this tub right here, so let's just get that out of there. Now there's a handy chemical rule for understanding dilutions. The moles of solute before dilution is equal to the moles of solute after dilution. Think about it, the total amount of hydrogen peroxide is going to stay the same, no matter how much water it's diluted with. But as you dilute a solution, its volume grows. The moles stay the same, and its molarity thus shrinks. To calculate precisely how much one affects the other, we use a standard and super simple dilution equation. Here, M1 and V1 are the molarity and volume of the original concentration, sometimes called the stock solution. In this case, what's in the bottle. M2 and V2 are the molarity and volume of the diluted solution. So in our case, M1 equals 0.88. That's the molarity of the hydrogen peroxide solution that we've got. And to bleach the stains out of laundry, we need a 0.1 molar solution. That's M2, the molarity that we want to get to. And the tub that I'll be soaking my whites in holds 38 liters of liquid, so that's our V2. All that's missing is the volume of peroxide solution that we must add to 38 liters of water to get to our target molarity. Do the math and you get V2 equaling 0.24 liters of hydrogen peroxide, or 250 milliliters. And we just fill this right on up here. Hopefully we have enough. And that's what we need. And while I wait a few hours for the peroxide to do its work, I'm going to enjoy another of my favorite aqueous solutions, tea. Today here at Crash Course Chemistry, we learned about some of the properties of water that make it so special, its polarity and its dielectric property. We learned how electrolytes can be used to classify solutions, and we discovered how to calculate a solution's molarity, as well as how to dilute a solution using the dilution equation. This episode of Crash Course Chemistry was written by Kim Krieger, the script was edited by Blake DiPastino and myself, and our chemistry consultant is Dr. Heiko Langner. Our director, cinematographer, and editor is Nicholas Jenkins. Script supervisor is Michael Aranda, who also is our sound designer, and our graphics team is Thought Cafe. It falls from the sky. It makes up 60% of our bodies, and just about every chemical process related to life takes place with it or in it. Dihydrogen monoxide. Without it, none of the chemical reactions that keep you alive would happen. None of the reactions that sustain any life form on Earth would happen. Not even the majority of inorganic chemicals. You might use a solution of sodium hypochlorite, better known as bleach. What makes bleach so good at its job is that it's a really strong oxidizer, meaning that the oxygen atom is really good at pulling electrons away from other compounds, making them break apart. This is really handy for getting rid of stains, but as you can tell by the formula, sodium hypochlorite also contains chemical reactions that shape the surface of the Earth would happen. Water is the key to nearly everything, and one of the reasons it's the key is because it's really good at dissolving stuff. We need it so bad that we dump over 180 gallons of it into our bodies every year, and we do that in order to maintain an aqueous or water-based solution inside our cells, because aqueous environments are pretty much the best for cool chemistry. Each and every one of us uses water for all kinds of chemistry every single day. Our body chemistry, our food chemistry, and yes, our laundry chemistry all take place in water. Ugh. This used to be a white sock. It is now a little bit of gray sock. And in places a little bit of a yellow sock. But anyway, I want it to be white again, and to do that, I'm gonna need some chemistry. To whiten white,